All right, everyone, last but not least, part 3 of factorial analysis of variance in SPSS. We're going to go over in a little bit of an abridged way the second illustrated example from chapter 8 of the Pink Book. It begins on page 105, and you can find this table, table 8.2, which goes with the data file data_8_2.sav on page 106. So, without further ado, a researcher wanted to examine the impact that room temperature has on exam scores of students sitting in a first-year economics exam. So she believes that there would be a difference in exam scores between students in hotter rooms, and by hotter she means 29 degrees Celsius, and students in cooler rooms, by which she means 23 degrees Celsius. Additionally, she believed that exam difficulty would influence the impact of room temperature on exam scores. So she gave these poor students two different versions. So students are either taking the exam in a hot room or a cool room, and they're either taking an easy version or a hard version. So she asked 40 participants to take part in the study. Participants were divided into 4 evenly sized groups. 10 participants who completed an easy exam in a cool room, 10 participants who were asked to complete a hard exam in a cool room, 10 participants were asked to complete an easy exam in a hot room, and 10 were asked to complete a hard exam in a hot room. Then the exam scores for these participants were compared to answer 3 basic questions. Does room temperature influence exam score? That is there a main effect of room temperature? Does exam difficulty influence exam score? That is there a main effect for exam difficulty? And finally, does the influence of room temperature on exam score depend on the difficulty of the exam? In other words, is there an interaction effect? So here are our 3 groups with the little note at the bottom specifying which group experienced which conditions. I'm glad they specified 23 degrees versus 29 degrees because I would have a hard time even imagining what your directional hypothesis might be just based on cool and hot. But really what they mean is sort of cool versus normal temperature. And so in that case, I can imagine I would much rather take an exam in a 23 degree room than a 29 degree room. All right. So what I'd like you to do now is pause the video and think about what's the research questions. I know we just read them, so maybe that's not an interesting question. What are the independent variables or predictor variables? What's the factor notation for this study? What's the dependent variable? And what's the null hypothesis? Welcome back. So my condensed version of those 3 research questions is what are the separate and combined effects of temperature and exam difficulty on exam performance? And what follows from that is that the independent variables are temperature, that is 23 or 29 degrees, and difficulty, that is, was it an easy exam or a hard exam? This is a 2x2 factorial analysis of variance. The dependent variable is exam score, and the null hypothesis is that exam scores were the same for all groups. Just as a reminder, here's how we might organize our table. So here are our sample sizes in each cell, and you can imagine adding marginal means to the ends of each row and column of data, and then also a grand mean. Okay, so let's take a look at the data. Find data file data_8_2.sav. So here we are. This time we do have a participant ID. So that first variable is participant ID. Then we've got the temperature with 1 indicating the cool room and 2 indicating the hot room. And difficulty, again, 1 indicates easy and 2 indicates hard. And then our dependent variable, the score, is a scale variable. All right, to check assumptions, I'm going to do the same thing that I did before. Recall that we've got the same assumptions that we did before. Level of measurement, is it an interval or ratio scale variable? For all intents and purposes, yes. Is there independence of observations? As far as we can tell, there is. There's no evidence otherwise. Are the data normally distributed? Now, we want to look at each of those 4 groups separately to evaluate whether they're normally distributed. So in order to do that, I'm going to add a cell column to this data set. But if you want to do it by splitting the file, you're welcome to do that too. So I'm going to compute a new variable, call it cell. Remember, they're both coded as 1s and 2s. So I'm just going to take temperature and multiply it by difficulty plus 1. So now I have 1 and 2 for temperature and 2 and 3 for difficulty. And click OK. Now you can see if they were in the cool room and they got the easy exam, they're coded as 2. Cool room, hard exam 3. Hot room, easy exam 4, and hot room, hard exam 6. So I'm going to go into variable view and add those values. So there we go. Now if the temperature is cool and the difficulty is easy, the cell variable says cool and easy, just to make it a little bit easier when I actually analyze these things. So analyze, explore, exam score is my dependent variable, and I'm going to use cell in my factor list. I'm going to not look at the stem and leaf plots, but I am going to look at normality plots. I'm just going to skip over the descriptive statistics and look at our statistical tests of normality. So what we see here is the cool, easy condition suggests that there's a violation of normality according to the Kolmogorov-Smirnov test. And if we look at the Shapiro-Wilks test, both cool, easy, and cool, hard. So all the participants who took the test in the cool temperature, so the regular temperature, it looks like there's a violation of, or a potential violation of normality. So we want to go and look at our QQ plots. I'm on the fence, particularly about for this QQ plot, the students who took the hard exam in the cool temperatured room. But both of these seem to have similar violations of normality. Specifically, they've got outlier low scores, which you can tell from the box plot. So what I would probably consider in this circumstance is doing a two-way Kruskal-Wallis analysis of variance. This is sort of similar to it's the same idea as the one-way Kruskal-Wallis. It's a non-parametric equivalent to factorial analysis of variance. Or I might do a multivariate analysis of variance, which is something you're going to learn about in a subsequent stats class. But just for the sake of practicing using SPSS to conduct factorial analysis of variance, let's go ahead and do that. So even though I would probably do a non-parametric test on the basis of these results, I'm going to analyze, choose univariate. Exam score is my dependent variable. Room temperature and exam difficulty are my fixed factors. I'm going to look at options. I want to look at both main effects and the interaction. I want to display those means. I want to compare main effects. I want to see descriptive statistics, estimates of effect size, homogeneity tests, and nothing else. I'm not going to monkey with the significance level here because I can't do it for some tests but not others. So I'm going to click continue. I'm also going to look at plots. So just like I did in example 1, I'm going to look at two versions of the same graph. So I'm going to have temperature on the horizontal axis and difficulty as separate lines. And then I'm also going to look at difficulty on the horizontal axis and temperature as separate lines. As I said last time, you would never include both of these graphs in your results, but I like to look at both of them because different versions of the same graph will make different results clearer. So I'm going to continue. We could look at simple effects, but actually in this case we don't need to because we only have two levels of each independent variable. So we'll talk a little bit more about that when we get the results. So let's click OK. And here's all of our output. We've got descriptive statistics, we've got a Levine's test, we've got an ANOVA source table, we've got some estimated marginal means for room temperature and for exam difficulty. And for the interaction, notice we don't have any simple effects. And I've got two different graphs. So let's start by looking at these descriptive statistics. We've got means and standard deviations for each group. We've also got total means and standard deviations for the cool room, regardless of whether the exam was easy or hard, and the hot room, regardless of whether the exam was easy or hard. And then we've got the overall easy exam mean score and the overall hard mean exam score, regardless of what temperature it was. Now what I would like you to do is see whether you can take those numbers and put them into this factorial table of cell means. Again, if I haven't said so already, this is not a table you would probably include in a results section. It's just a way of organizing your thinking to help you to see what the effects are. Okay, give it a shot. Is this what you got? Before we move on to inferential statistics, I just want to talk about this graph. Now, as you recall, there was another profile plot included because I like to look at them two ways, but let's just look at this one in the interest of time. So based on the profile plot, do you think you can guess which F ratios might be statistically significant? I'm going to say that there's probably going to be a main effect of difficulty because I can see that there's a negative slope, right? If there was no effect of exam difficulty, we'd expect both of these lines to be pretty flat, but they're not. They both slope downward. I might predict, based on this graph, that there is no main effect of temperature because the lines are relatively close together. But again, this is something that I would have a hard time telling because there's no error bars, so it's really difficult to say. It's clear that the effect of room temperature is much smaller than the effect of exam difficulty. So just from looking at this, I would probably decline to make a definitive statement about whether it's statistically significant or not. The last thing we want to look at is there a difficulty by temperature interaction? And from looking at this, I would be very confident to say that no, there's no interaction. I can tell that because the green line and the blue line are parallel. So if the lines are parallel, that means there's no interaction. Here's our output. We can tell from the Levine's test that the assumption of homogeneity of variance was not violated. We have 3 and 36 degrees of freedom, an F ratio of only 0.62, and then a p-value of 0.61. So then, just as before, we're not so interested in looking at are the cell means different from the grand mean? Is the overall model statistically significant? We're definitely not interested in looking at is the grand mean significantly different from 0. So we're going to skip to the third row of our ANOVA source table. And what we can see from that is that there is a main effect of temperature. So that's the one that I wasn't sure about. we've got an F ratio of 6.13. We've got 1 and again 36 degrees of freedom with a p-value of 0.02 and an effect size of almost 15%, 0.15. So there's a main effect of temperature. There's also a main effect of difficulty. And you probably noticed that the effect size for difficulty is much, much bigger than the effect size for temperature. The last thing we want to notice is, as we suspected, there is no temperature by difficulty interaction. So we've got an F ratio of 0.029, so 0.03, and a significance level of 0.866. Now, so we actually don't have any further analyses to do because we've only got a 2x2 design, so there's no sort of breaking down of these effects that is necessary. Based on the fact that we got a significant effect of temperature and that the test scores for the hot room were lower than the test scores for the cool or normal temperature room, we can report that students tested in a hot room scored significantly lower than students tested in a cool room. We can also report that students who were given the easy test scored significantly higher than students who were given the hard test. No surprise there. We would certainly be concerned if that were not the case. And we can report that there was no interaction. And I've added the F ratio here with the p-value because it's becoming more common, at least in my experience. I'm getting editors asking me to report all of the F ratios that I calculated, even if they're not statistically significant. And the reason for this is sort of the same reason we ask for confidence intervals and effect sizes, and it's in the interest of completeness. Don't just tell me that it wasn't there. Show me how not there it was. And if you're interested, take a look at pages 107 to 108 of the Pink Book for details on how you'd write this up in APA style. The last thing for now is that if you haven't already saved your output file for example 2, please do so. I hope you enjoyed our little foray into factorial analysis of variance because you have more of it in your future. All right, thanks everyone. Bye for now.